reforming. And what you will learn in this module is actually how these reactions and the catalyst on which these reactions are carried out in the industry. What is the reactor configuration? The various process variables and their effect on catalytic reforming. As you know, the various reactions that happen, there is a compromise in terms of desirable reaction versus undesirable reactions. So the process variables play a very key role. And in the industry today, we have two major type of reformers. One is called as a semi-regenerative reformer, and the other is called the continuous catalytic regeneration reformer. Actually, the name of these two reforming technologies actually is because of the way we actually regenerate the catalyst. In a semi-regenerative reformer, we don't actually continuously regenerate the catalyst. It is done, let's say, once in a year or once in 14 months. While in continuous catalyst regeneration reformer, we actually continuously regenerate the catalyst as the reaction goes on. So we will talk about all of them. So by the end of this module, you'll learn exactly how catalytic reforming is carried out. But this, picture, this schematic actually tells you typically how we do catalytic reforming in the industry. So you got the feed coming in, the naphtha, and it is pumped along with our recycled hydrogen. So I'll come back to this point later on again. But this is actually the recycled hydrogen being compressed along with the feed. It goes through a heat exchanger to preheat the feed along with the gas, along with the recycled gas. And then the rest of the heat is provided by a furnace, which is a fired furnace, similar to what we learned in the crude unit and the vacuum unit, the crude furnace and the vacuum furnace. So here also you have flames here, and you have a convection section and the radiation section, all of it. And of course, you have a preheating of air so that the adiabatic flame temperature is higher. To that extent, the furnace efficiencies are high. So the feed is preheated to something like 530, 520 degrees Celsius, but it is always above 500. And then it passes through the first reactor. In the first reactor, what happens, as I'll show you in the next slide, because of the endothermicity of the reaction, the temperature drops. And the drop could be as high as 60 to 70 degrees Celsius. Okay. And after that, we need to actually do the further reaction. So it's actually put into another furnace. This is called as an interheater. This is called as a feed furnace, while this is called as an interheater because it is between these two reactors. And the product and the outlet from this furnace goes into a second reactor, where actually again the reactions take place which are endothermic. And so you get a drop in temperature again, which is actually recovered back again in the furnace, in the third furnace, which is again an interheater, and then into the third reactor. So generally we have a 3-reactor configuration, and I'll explain to you why we have a 3-reactor configuration. There are a few reforming units. In fact, one is there in our own country, in Bongaigaon refinery, which is called, it is called Bongaigaon refinery today. It is actually the refinery is owned by Indian Oil, and they have actually a 4-reactor unit, but that unit is now converted to isomerization unit. It is no longer a reforming unit. So this feed actually goes into the reactor, and this reactor outlet is pretty hot. It is above 500 degrees Celsius. So we need to recover this heat, and this heat is recovered by preheating the feed. And so this is called as a feed effluent heat exchanger, as you see, F_E. And this is typical. In fact, you will see more of this discussion as we go along in other technologies, where the product coming out of the reactor, the final product coming out of the reactor, is actually cooled against the feed coming to the unit. Okay, so it is called a feed effluent heat exchanger, and then the product is further cooled, and then the uncondensed gases go out, which is predominantly hydrogen, and some amount of C1, C2, and that part of it is recycled back. Why do we recycle this hydrogen back? Is basically in order to maintain a strong hydrogen atmosphere right across, in order to suppress the coking. Of course, as you go through the reactors, more and more hydrogen gets generated because of the reactions that we talked about, cyclohexane converting to benzene, etc. But initially, when we enter the reactor, it should be actually at those temperatures. If I don't put any hydrogen, this feed will crack at 500 degrees Celsius, right in the furnace itself. So the hydrogen is present in order to actually make sure that the partial pressure of hydrocarbons is kept low, and so that the cracking is suppressed. As far as the three reactors are concerned, this is how they actually operate. The first reactor, as you can see, what you see on there are two graphs here. The first graph is actually the reactor temperature. So you can see that when we enter at T0, that is that is the inlet temperature to the first reactor, there is a drop in the temperature, almost like 50 to 60 degrees Celsius. And most of the reaction that happens here is actually the dehydrogenation of naphthenes. So the first reactor, because that is a fast reaction, and it is actually promoted very strongly by the metal site of the catalyst, and it's highly endothermic. Okay, so basically, this first reactor does more of it is not that it doesn't do other reactions also, but the dominant reaction in the first reactor is the dehydrogenation of naphthenes. And since it's a highly endothermic reaction, there is a significant drop in temperature, something like 50 to 60 degrees Celsius. And then actually you heat it up again, right up to the same temperature as which we entered the first reactor. And then you see that this particular endotherm is not that high because most of the naphthenes got converted, and then now you have dehydrocyclization of paraffins happening, which again gets converted to naphthenes and then to aromatics. So basically, the amount of endotherm is not that high. Nonetheless, there is a drop in temperature in the second reactor as well. And then we go into the third reactor where actually sometimes there is no change in temperature because here whatever endothermicity is there is actually compensated by the exothermicity of the hydrocracking reaction. But nonetheless, we have a third reactor in order to make sure that we don't have any naphthenes passing through into the product stream, because any naphthenes passing through to the product stream is an implicit loss of aromatics. And if you look at the composition profile of paraffins, naphthenes, and aromatics, so this is actually the feed composition: 60% paraffins, 30% naphthenes, and 10% aromatics. This is the straight term naphtha composition. So N plus 2A is like 50 here, which is pretty low for a typical reformer feed. So you can see that as we enter the first reactor and as the reactions happen in the first reactor, the naphthenes actually start dropping down. And to that extent, the aromatics actually go up. The paraffins roughly remain the same. Then in the second reactor, the hydrodecyclization of paraffin kicks in. So the paraffins start dropping in, and they continuously keep on dropping as we go right across the third reactor, while the aromatics keep on building up. And these paraffins, when they converted to naphthenes, they get converted to aromatics. So the life of the naphthenes, when you convert from paraffins to aromatics, is not that high. So ultimately, this is the residual naphthenes, which is still present around 1.5% in the product going out. So this is actually the product composition. This much amount of aromatics, paraffins, naphthenes, and this composition you have already seen, which I discussed in the part one of catalytic reforming. Now, in order to actually promote these various reactions, what we also do is that we try to actually distribute the catalyst in the order in which the reaction is required to be done. So before I come to this table above, the catalyst distribution, let me discuss this table below. If you look at the four major reactions that happen, that is the naphthene dehydrogenation. Actually, if you take the paraffin dehydrocyclization, rate of reaction as 1. Okay, so that is, if you take that as a base, then naphthalene dehydrogenation is 30 times faster. And since it is 30 times faster, we don't really need a large amount of catalyst in the first reactor, which is actually doing the dehydrogenation of naphthalenes. So that's why in the first reactor, we only put 10% of the total catalyst. Okay. If you look at the isomerization in terms of either isomerization of paraffins or naphthenes, the rate of reaction is 3, which is of the same order of magnitude as paraffin dehydrocyclization. And cracking, of course, is half that of these reactions. So we actually suppress this, as you know, by putting hydrogen. And so actually, the second reactor, we fill up almost like 15% of the catalyst. This is, of course, for a 4-reactor configuration. But if suppose I don't have 4 reactors, and if I have only 3 reactors, then the distribution could be something like 20% of the catalyst in the first reactor, followed by something like 40% in the second reactor, and then the balance in the third reactor. So 20%, 40%, that makes it 60%, and then 40% or 10%, 15% restless. So actually, this 50%, which is in the fourth reactor, gets distributed between these three. And the ratio is generally 1:2:3. That kind of a ratio we keep in order to have more catalyst in the third reactor. The largest amount of catalyst is in the third reactor because of the low rate of reactions. And we would like to actually have these reactions completed before the products come out. So all the reactions that we discussed, they occur in series and parallel to each other. Series is actually the dehydrocyclization of paraffins. And so this is actually a good slide for you to understand that according to the rates of the reaction, the main reaction in the first reactor is actually the dehydrogenation. The one in the italics is something which is dominant. So dehydrogenation is the dominant reaction in the first reactor, and isomerization also starts because the rate of reaction of isomerization is slightly higher than paraffin dehydrocyclization. Then in the second and the third reactors, we have dehydrogenation still going on of the naphthalene, isomerization as well, and then the cracking starts happening and the dehydrocyclization kicks in, and they can kind of complete in the fourth reactor. So if there are 3 reactors, then actually in the second and the third reactor, this kind of operations happen. But in the first reactor, we don't really see much of dehydrocyclization or cracking actually. It's basically dehydrogenation and a little bit of isomerization of paraffins. Now, having seen that, there are 6 variables in a catalytic reforming technology that we need to actually, be aware of. And all of these 6 variables are extremely important in order to actually leverage the advantages of these variables in terms of the end product yield and the product property that we want to achieve. Out of this, the reaction temperature is by far the most important. Because the reactions are endothermic and we need to have a temperature at which those reactions happen at a pretty fast rate. And there are 2 definitions as far as the reaction temperature is concerned, because there is no one reactor, there are 3 reactors. Okay, so we need to define what exactly do we mean by the reaction temperature in catalytic reforming. It is there are 2 definitions. One is called as the weighted average inlet temperature. This WAIT stands for weighted average inlet temperature. And that is very simple to understand. It is the weight of the catalyst in first reactor into the inlet temperature in the first reactor plus weight of catalyst in the second reactor into the inlet temperature in the second reactor and the third reactor. Generally, we don't have 4. So basically, this is sum total upon the total weight of the catalyst. So this gives you a kind of a average inlet temperature, so as to say. And this is actually a representation of the severity of reforming. in the sense that actually if I go up on the inlet temperature, I actually increase the severity of reforming. To that extent, I can increase the octane number of the product if I'm making gasoline, or I can increase the aromatic yield or aromatic content of the reformate if I'm actually carrying out a reaction to make aromatics. So I hope this is clear. Weighted average inlet temperature is nothing but the individual weights in each reactor into the inlet temperature and sum total overall reactors upon the total weight of the catalyst. There is another definition which is called as the weighted average bed temperature, where actually we take the inlet temperature and the outlet temperature and divide it by 2. So it is actually a kind of a mean average temperature in the bed, T1 inlet plus T1 outlet upon 2 into the catalyst weight. So the only difference is that rather than taking the inlet temperature, we take an average between the inlet and the outlet. Rest of it remains the same. So this is sometimes we use this terminology. In fact, most of the time, weighted average bed temperature actually gives you more idea as to what is the severity at which we are carrying out the reaction. Weighted average inlet temperature is more actually if there is an advanced control system operating on the unit, and that advanced control system actually tries to maintain a certain weighted average inlet temperature as given by the operator by manipulating the by manipulating the furnace duties. So these are the two definitions, but just to give you an idea as to what happens if I increase the weighted average inlet temperature. So if the operator starts setting a higher set point to weighted average inlet temperature, what will happen is that, of course, the severity of reforming goes up. In other words, I do get an increased octane. But because of the increased octane, my C5 yield goes down because more cracking also takes place and more hydrocracking takes place. So the total liquid yield goes down and I get more of C1, C2, C3, C4. So LPG yield goes up. And because of the presence of C1, C2, the hydrogen purity is also reduced. Remember, I mentioned that catalytic reformers in refineries is also a source of hydrogen. And not very many years ago, it was the only source of hydrogen in a refinery because the refinery still did not put hydrogen plants to produce hydrogen because there was no spec on sulfur, etc., on all the fuels that we were using. So when the fuel specification starts to kick in, both for gasoline and diesel, then the refineries in India started putting hydrogen plants. So we had actually an on-purpose hydrogen unit starting in the refinery. But otherwise, the hydrogen is a byproduct from this unit, and the purity of hydrogen therefore becomes important. But if you increase the weighted average inlet temperature, that means if you're increasing the severity of reaction, then to that extent we get impure hydrogen. And of course, it increases coke deposits. So it actually promotes those two adverse reactions, hydrocracking and forking. So basically, there's a kind of a compromise between to what extent you should go and to what extent you would not like coke deposit, etc., etc. Now, so you can understand that if suppose I have a technology like semi-regenerative reforming reaction, where I actually regenerate the catalyst in once in a year, I would not like too much of coke deposit. So generally in those type of reformers, I will not go high temperatures. But in a CCR type of reformer where I'm continuously regenerating the catalyst, it makes more sense actually to go up at a high temperature because if there's a coke deposit, at the same time I'm regenerating the catalyst as well. So CCR reformers have actually helped us to go up on weighted average inlet temperature. And this is just a formula. So to increase 1 unit of octane, you need to increase 3 degrees rise in temperature. Generally, this is the temperature working range. This is already going up actually now. Sometimes we operate at 530 as well, so that we take advantage of the higher octane or higher aromatics. If you look at the second variable, if you recall, the second variable was space velocity. Actually, space velocity you cannot really do much about, because if the unit is operating at a certain throughput, that decides the space velocity. Space velocity is nothing but the total superficial velocity of the entire feed going through the reactors. And that is the sum total of the liquid flow, that is the feed flow, the naphtha flow, which of course gets vaporized in the feed effluent heat exchanger. Naphtha is not in the liquid form when it goes through the reaction. It is all vaporized. Plus, of course, the recycle flow, the recycled hydrogen. So the sum total of these two flows through the catalyst is actually what is called as the space velocity. And how do you calculate the space velocity? It is actually the volumetric flow rate, that is the total meter cube per hour of the total feed, that is the naphtha plus the recycle, upon the volume of the catalyst, total volume of the catalyst. And this is the bulk volume. I'm not talking about the actual volume of the catalyst. It is the bulk volume. So if you take the catalyst and fill it in a measuring cylinder, 1 liter or whatever it is, that is, so it is actually what we call as a bulk density, including the interstices volume. So that is basically what is called as a linear hourly space velocity. And this is actually, the unit is 1/hour, because the volume cancels out. The other definition of space velocity is the weighted hourly space velocity, which is nothing but the feed in terms of kg per hour upon the total weight of the catalyst in kg. So this is like 1/hour again. And so generally we operate these reformers in the range of 1 to 3 LHSV. Now, going back to the previous slide, if you actually reduce the space velocity, that means if I, for the same reactor configuration, for the same reactor volume, for the same reactor size, if I actually start putting lesser flow rate, lesser feed, what happens is that actually my space velocity goes down. And the lower the space velocity, the higher is the severity, because the residence time goes up. So the space velocity is related to the residence time or contact time. So the higher the space velocity means there is less contact time of the feed with the catalyst. And that way, actually, the reforming reactions, the amount of reactions happen will be less. The amount of conversion happening would be less. But if I reduce the space velocity, in other words, I increase the reaction time or the contact time, I end up actually increasing the octane. The effect is the same as temperature. So either you increase the temperature or you drop the space velocity. The effect is the same, as you can see. You decrease the liquid yields, you decrease the hydrogen purity, and you increase the coke deposit. It is exactly the same that you see here. Increase octane, decrease yield, decrease hydrogen purity, increase coke deposit. So temperature and space velocity, they are actually opposite to each other. Either increase in temperature or drop in space velocity. Both ways, actually, you increase the severity of reforming. And thereby you actually increase the octane yield. You increase the octane, but you actually reduce the yield. So many times, actually, we use a variable like octane barrel. What we mean by octane barrel is actually the octane into the amount of into the barrels per hour of liquid yield. Okay, so that is more important. It's actually having a very high octane in the product, but very low yield of that product. It doesn't matter. It doesn't make any sense. Okay, because it is not the octane. It is the total amount of high octane material that we are interested in. So it is called octane barrel, the product of octane number into the volumetric flow of the liquid product that you get out of the reformer. So that is something that we try to maximize, and that actually enables us to, uh, operate the reformer at the optimum combination of temperature and space velocity. So here you can see what this is what exactly I meant actually. If you plot reactor inlet temperature versus LHSV, this line actually gives a relationship which says that for every rise in LHSV of zero point 0.1 between 1 to 2, that means the higher the space velocity, you need to go up on temperature in order to compensate for the less reaction or residence time. And this is plot is for a feed containing N plus 2A of 69. So I think yeah, it's very important to understand, and actually, ultimately, in the real operations, we really don't have much handle on LHSV because the idea is always to push maximum throughput through the reactor through the unit. So the operator always try to push maximum flow rate given the constraints of the pumps, compressors, pressure drop across the reactor, etc., etc. So LHSV is always at its lowest actually, at its highest, because it's the high space velocity. And whatever then octane barrels that we would like to get, that is the only handle available with the operator is the weighted average inlet temperature. If you look at the effect of reaction pressure, pressure is the most important variable. If you recall, when I talked about catalytic reforming, I mentioned that when it was invented by UOP way back in 1942, the first commercial unit operated at almost as high as 70 bar, 70 kg per square centimeter. Ever since, actually, there has been a kind of a drive to go down on pressure because actually there's an expansion in volume when you do dehydrogenation. That means naphthalene is going to aromatics plus liberation of hydrogen. So there is an expansion in volume. So according to Le Chatelier's principle, it is better if you go down on pressure. And so there has been a continuous, effort to go down on pressure. So almost from 70 bar in 1949, today's reformers are designed at about 3.5 kg. But 3.5 kg, you cannot design a semi-regenerative reforming because the pressure reduction that increases the dehydrogenation of naphthenes and dehydrocyclization because of the Le Chatelier's principle. But on the other hand, it increases the catalyst coking, and so the catalyst has a shorter life, and so you actually have to get into the regeneration immediately. So we take advantage in the CCR reformers of continuous regeneration by dropping the pressure. But in semi-regenerative reformers, where we want to actually decoke, let's say once in a year, we operate at a higher pressure so that the coking rate is suppressed. So higher pressure actually causes higher rate of hydrocracking, so it reduces reformate yield, but decreases coking of the catalyst. So again, there's a compromise between coking and hydrocracking. So in low pressure operations, like in CCR reformers, we take advantage of a lower pressure. But actually at a lower pressure, we suppress the hydrocracking. But actually the coking goes up. And that's okay because then we have a continuous regeneration anywhere. The last line is extremely important for you to understand and realize that the pressure is not actually in the hands of the operator. Actually, if the unit is designed for a certain pressure, it has to be kept the same way throughout the life of the unit. Because actually the unit is not a standalone. I mean, the reactors are not standalone. You've got a compressor, the recycled gas compressor. If you go back, there are other process equipment here. The separator pressure, the separator drum, the heat exchanger, the furnaces, the pump, the compressors, etc. And they are designed for a certain pressure. So actually, if I have designed the whole system for let's say 15 bar, and I try to drop it to 3.5 bar, now this is coming down to 3.5, so the volume goes up, and this compressor may not be designed to handle that extra volume. Okay, and similarly, actually, so basically, when you go down on pressure, the recycled gas compressor is the first one, which actually gets into a constraint. And the rest of it, of course, in terms of the higher space velocity, the volumetric flow rates go up as you go down on pressure. So the pressure drops in the reactors go up. So actually the size of the reactors have to be different. Okay, if you are operating if you are actually designing this unit for a low pressure operation. So the 3 bar and 30 bar means there's an order of magnitude difference. So 30 bar, the reactor sizes will be much smaller as compared to when you design it for 3 bar, because there's a 10 times expansion in volume. If you remember your ideal gas law, PV is equal to nRT. And so actually, coming back to the effect of pressure on reformate yield, as you go down on pressure for the same octane, my C5 plus yield goes up. So actually, what I meant by octane barrel, now you can see very clearly, if my liquid yield is 85 or something like 80%, and my octane is 100, that is called as the octane barrel, 100 into the yield of the liquid yield. I mean, when you actually take out the reformate, you condense the reformate, and whatever doesn't condense actually is the gaseous product which goes along with the hydrogen stream. Then we recover the LPG from there, the C3, C4. But whatever condenses is actually called as a liquid yield, and that liquid yield into the octane is actually called as an octane barrel. So the higher the pressure, for the same octane, you get a lesser yield because of increased hydrocrack. So these are the typical yields that you see as you go from 24 to 10 bar in the same reactor. Of course, this kind of a range of operation is typically not possible in an operating unit. So actually, you can see that the C5 yield has an immediate hit actually. So if you go down on pressure, your yield goes up, and this is the advantage that we take care. We actually try to take advantage of this in CCR reformers. So we get a higher liquid yield, but on the other hand, we get a higher coke deposit as well. So that, of course, we actually compensate by continuous regeneration. Okay, the third variable is actually the hydrogen to hydrocarbon fourth variable. So we talked about temperature, we talked about space velocity, we talked about operating pressure. Now the hydrogen to hydrocarbon ratio. So you remember when I started off the schematic of this unit, I said that there is a recycled gas, and this is rich in hydrogen. So when we say hydrogen to hydrocarbon ratio, we are talking about this flow rate, that is this recycled gas flow rate upon this fresh feed flow. And that is actually the hydrogen to hydrocarbon ratio, or the recycled gas to feed ratio. And this ratio is maintained at a certain number in order to suppress coking. So hydrogen to hydrocarbon ratio is the moles of hydrogen in the recycled gas upon moles of the feed, the hydrocarbon feed. And the main purpose, as I told you earlier, is to increase the hydrogen partial pressure in the reaction. And that is to suppress the coke formation, because the hydrogen reacts with the coke precursors, removing them from the catalyst surface. And thus, we actually make sure that the catalyst sites are active. And so the higher the hydrogen to hydrocarbon ratio, higher is the cycle length. So generally in semi-regenerative reformers, as you must have guessed by now, we try to keep a higher hydrogen to hydrocarbon ratio because we want to suppress coking, because we'll decoke only after about a year or so. But in CCR reformers, since we are regenerating the catalyst on a continuous basis, we can reduce the hydrogen to hydrocarbon ratio. By reducing the hydrogen to hydrocarbon ratio, what you do is that actually you reduce the space velocity as well, and that way actually you provide more residence time, and thereby you actually increase the severity of reforming as well. So the advantage of effect of reduction in hydrogen to hydrocarbon ratio. So the operator always tries to minimize the hydrogen to hydrocarbon ratio subject to the constraints in terms of coking. So that it actually, if you reduce it, of course, helps in energy cost for compressor, which is circulating that recycled gas. And of course, you have a less pressure drop in the reactors, and favors naphthalene dehydrogenation because actually naphthalene dehydrogenation produces hydrogen, and it's an equilibrium control reaction. So if you have less hydrogen in the feed, to that extent, you reach equilibrium towards the right, that is towards benzene. The disadvantage is, of course, effect of loading from 8 to 4, your coke yield goes up. So this is what actually we try to avoid in semi-regenerative reformers, and that's why there so the typical numbers that we operate is roughly about 4 hydrogen to hydrocarbon ratio, mole by mole. And in case of CCR reformers, it could be something as low as 2.5. Um, the fifth variable is the feed quality. Of course, generally this is dependent on the crude, and sometimes some refiners actually buy a higher naphthalene, naphtha from the market. Of course, naphtha containing higher naphthalene may not be so cheap. But of course, nonetheless, it's a good feedstock for catalytic reforming. So naphthenes, of course, as you know, dehydrogenate very fast. So N plus 2A is taken as an index of reforming. Higher the N plus 2A, the better the quality of the feed is, because it will give you higher aromatics. Lighter naphtha fraction, of course, something like light naphtha, which is dominantly C5, C6. They generally have less naphthene, because naphthene starts with C5 carbon number. But at a lower boiling range, you have less naphthene. So that actually is not a very good feedstock. And if suppose if you have a C5 fraction which contains only paraffins, isoparaffins, and naphthenes, that is definitely not a good feedstock at all. Because the reforming for reforming to make aromatics, you need at least 6 carbon numbers. So actually, if you keep a lower boiling point of the feed, and you have significant quantities of C5 coming along with the feed, that will by default result into lower aromatics and lower hydrogen yield, because they just have a merry ride through the reactors. While on the other hand, if your endpoint goes up, so we discussed about the initial boiling point, it should be as high as possible. Generally, we keep roughly at about above 95. In Reliance, we keep it at 105, because here we are not making gasoline from reformer. We are actually making paraxylene. So the xylene fractions, actually, like the paraxylene, metaxylene, orthoxylene, and the ethyl benzene, the C8 aromatics, they boil in that range of about 135 to 142. So we keep that boiling range so that we have all the precursors in the feed to make paraxylene. But heavier fractions, like we try to minimize the heavy fractions, like we keep the endpoint below 160. Because the heavier fractions have then you get two ring aromatics coming in, like naphthalenes, etc. And you get higher coke formation. So up to C10 is okay. We don't go beyond C10, carbon number 10. So from the other end it is C6, and from the other end it is C10. So actually the feed to the reformer is a kind of a sharp cut, or what we call as a hard cut, which is C6 to C9 generally, a little bit of C10, whatever gets in terms of the overlap. And this is, of course, explains, this is no-brainer. This is the aromatics in the reformate versus octane, and you can see that as the feed goes from paraffinic to naphthenic, not only for the same octane, I get more aromatics in the reformate. As far as the feed is concerned, again, it depends upon what is the purpose of running the reformer. If suppose the reformer is being operated to make benzene, then actually we need to maximize the benzene precursors in the feed. So the feed would be something like a 60-90 cut. TBP 60-90 cut. 60 initial boiling point, 90 final boiling point, in that range. so that you have all the benzene precursors like cyclohexane, methyl cyclopentane, etc., by which you can convert them to benzene. If the reformer is designed to make toluene, then of course you have 90, 110 cut, because this particular cut will have all the toluene precursors. If you're looking at xylene, the way we do it, it's up to from something like 105 to 160 in that range. And if the reformer is making gasoline, then this 140 can go even up to 160 at the most, but we don't normally go beyond 160. Otherwise, the aromatics, the heavier aromatics, start actually becoming the coke precursors. Although the endpoint specification on gasoline is 210, but in the reformer, we don't go beyond 150, at the most 160. I mean, beyond, not beyond C10. And this is the effect of the various process variables that you see here. I think this you can, we have already discussed it in great detail. So, once you get a copy of this presentation, you can study it to study the effect of various variables on octane, reformate yield, and coke deposit. So, as you can see, some of them increase, some of them decreases. So, as I said before, all these variables we actually optimize to maximize the reformate yield, the octane, and to minimize coke deposit. As far as the reforming processes is concerned, I will, as I already mentioned, there are majorly two types of reformers in the industry today. The semi-regenerative reformer, which is actually, it has been actually, all around even today. But in today, if suppose you want to build a reformer, you would go with a moving bed or a CCR. ExxonMobil actually came up with what is called as a cyclic cyclic unit as well, where it is same as semi-regenerative reformer, but we have like 4 reactors, out of which 1 reactor can always be taken offline for regeneration. So what they try to do is that the entire unit is operating almost continuously, because 1 reactor is always in the regeneration mode. So here in the semi-regenerative reformer, the reformer process feedstock till catalyst gets completely deactivated, and then we shut the whole unit down for regeneration. So in a year, roughly about 20 to 25 days is taken up for a complete shutdown, making the unit hydrocarbon free, and then actually burning off the coke, and then regenerating the catalyst, and then actually putting the unit back online again. So in 1 year time, in about 13, 14 months, almost the unit runs for about 10 to 11 months, and for 1 month it is shut down. That is circumvented to some extent in the cyclic reformers, where 1 reactor is so whether semi-regenerative reformer has, if it has 4 reactors, 1 reactor is always isolated and in the regeneration mode. So any reactor which actually get cokes up will actually be taken off for regeneration. While moving bed, here the catalyst is moved continuously through the reactor. So it's like a slow moving bed. And the catalyst is then withdrawn from the last reactor. And then the catalyst is taken into another reactor where actually we pass air, in which the catalyst coke gets burnt off. So that is called as the regeneration section. And then the hot catalyst is returned back to the first reactor. So this is the way, this is the kind of a classification of different types of reformers. And the operating conditions are actually summarized here, where in the fixed bed or semi-regenerative bed, initially it started off with just a monometallic catalyst like platinum catalyst, then actually it became bimetallic, platinum plus rhenium. So semi-regenerative reforming had platinum plus rhenium. Initially, as you said, as you know, the pressures were 70 bar, but today, if you build a semi-regenerative reforming catalyst reactor, it will be something like 15 bar. We don't go below that, otherwise the coking goes up. The hydrogen to hydrocarbon ratio is reasonably high, around 4 to 6. And the space velocities are kept around 2 to 2.5, relatively high. and the octane you get is low, 91 to 98. I'm not going to talk about cyclic fixed bed because they are no longer in use, and there's not a single unit operating today, which is cyclic fixed bed. So moving bed CCR, which is a modern technology, is bimetallic, but here it is platinum and tin. The pressures are relatively low. Today, if you want to build a CCR reformer, it is 3.5 bar. As you can see, the hydrogen to hydrocarbon ratio is low, so that we have higher space velocities, up to about lower space velocities. And actually, the octane is pretty high. Having said that, it is not true that every time you build a reformer today, it has to be a CCR. It again depends upon the capacity. So if suppose I have a small refinery, something like a 3 million ton or 4 million ton or 5 million ton per annum unit refinery, the total naphtha production will not be that high. So something, there's a kind of a break-even number, like 300,000 tons per annum. And this number is going up actually, going down. But anything below 300,000 tons per annum or zero point 0.3 million tons per annum, generally people would go for a semi-regenerative reformer because it is too expensive to build a CCR reformer for such a low capacity. For higher capacities above 300, preferably 800 or 1 million ton, you would actually definitely go for CCR. So higher than 600,000 ton, no discussion. We will definitely go for CCR. Anything lower than 300, there's again no discussion. We go for semi-regenerative. Between 300 to 600, one can take a call in terms of whether you want to go for semi-regenerative or for CCR reform. So this is actually, I've already talked about this, the most commonly type catalytic reformer. In fact, when India went to completely unleaded gasoline, all the refineries built semi-regenerative reformers as such. So these refineries are tiny, these are small. In a refinery like Jamnagar, where you are processing in one single refinery 32 million tons of crude oil, the reformer capacity goes huge actually. So reforming capacity that is present in Reliance in a single refinery is almost of the order of around 5 million ton per annum. So there is catalytic reformers there. Of course, it is cyclic, continuous regeneration. Here, it is semi-regenerative. The most commonly type of used is semi-regenerative. This process is characterized by continuous operation over a long period. So it has something like a start of run and end of run. It actually, when you start with a fresh catalyst, the activity is quite constant for some time, and then it slowly reduces over a period of time. And then actually, once we know that it is economically unviable to operate the reformer, and as the activity goes down, the reactor temperatures have to be increased to compensate for the reduction in activity of the catalyst. And because of that, actually, we have to decide when we need to stop. So the decreasing the activity, the yield of aromatics and the purity of the hydrogen product decreases. And we actually raise the reaction temperature in order to compensate for the catalyst activity decline. So when it becomes, economically unviable, we actually shut down the reactor and the system and then generate the catalyst. How it is done? The whole unit is shut down, and then we actually pass air, dilute air. That means air containing almost 2 to 3% oxygen, no more than that. And then we actually burn off the catalyst slowly and regenerate the catalyst. So this generally, the semi-regenerative reforming catalyst is platinum rhenium. Because by rhenium, because it can tolerate high coke levels and it can regenerate easily. The rhenium helps us to actually suppress coke deposits. This is actually the flow scheme of a semi-regenerative reforming, very similar to what we discussed earlier. So you have the feed coming in, and then the recycled gas compressor compresses the hydrogen along with the feed into the furnace, and we preheat the feed. and then it goes into the first reactor, then into the interheater number 1, then into the second reactor, then the heater number 3, 2, then into the third reactor. And then the third reactor, when it comes out, you cool it. And here, of course, I've not shown the feed effluent heat exchanger, but this particular feed, before it enters this furnace, is actually preheated by this product. And then you go into the separator where you knock out the hydrogen along with the C1, C2, C3, C4. And then the liquid is taken out here, which is then stripped to take off the hydrogen out. And then you go through another stripper to take out all the C1 to C2. And then you fractionate this into like a debutanizer, where you take out the LPG, very similar to the naphtha stabilizer that I talked about, and you get the reformat. While here, actually, the hydrogen along with C1, C2, and some hydrocarbons, they go up here, and then it is compressed so that we actually knock out all the hydrocarbons which are coming along with this hydrogen. Here, actually, there are some operating conditions, but not so relevant for our discussion today. I think before I come to the CISA reformer,